Hey everybody. Today we're going to run through a few basic properties of the definite integral. We're going to justify them all with pictures only. The idea here is to build our understanding and ability to work with the definite integral without getting too deeply into the theory. So the first one that we're going to do is that if we integrate a constant over an interval a, b, we're going to get the constant times b minus a. So as always, let's remember that this notation here means that we're looking at the area under the graph of this function from this x value to this x value. Here's the picture. So let's label the two x values. And then I need to plot the graph y equals c. So that's a horizontal line, like so. I want the area under this graph between a and b. So from here to here, I want the shaded area. So this is a rectangle. The base is b minus a. The height is c. Base times height. C times b minus a is where this comes from. Property 2. The integral of a sum of two functions is going to be the sum of two separate integrals over the same region. So the integral from a to b, f of x dx, plus the integral from a to b, g of x dx. While we're at it, let's notice that this is also true for a difference, so plus or minus. So if I have an integral of two functions, I can integrate them each separately and then add the results. If I have the integral of a difference of two functions, I can integrate them both separately and subtract the results. This is very convenient as we get into harder problems later on in the course. Let's have a simple picture justifying this. So I'm supposed to have two functions, f and g. Let's go ahead and do a justification for the difference, f minus g. So in this case, just to keep it simple, I'm going to draw f higher up. Again, we're supposed to be going from a to b. So the graph of f might look like that, who knows? And just to keep it simple, I'm going to draw g as a straight line. But of course, this is going to hold for any function g that we can draw. Okay, so then the integral of the difference is going to be this area. What we're saying here is that this shaded area is equal to the area under f from a to b, so that's all of this, minus the area under g of x from a to b, so that's this area. So visually, at least, that's pretty convincing. Property 3. If I integrate a constant times a function, here c is still a constant, I'm going to get the constant times the integral of the function. Essentially, the constant can be factored out of the integral much in the same way as it can with derivatives. So again, let's have a simple picture. Let's do it just with a rectangle. So as always, I'm going to label the interval a to b. And I'm going to first label a graph of the function y equals f of x. I'm trying to compare y equals f of x and y equals c f of x. So multiplying a function by a constant is a vertical stretch. or compression if C is less than 1. I'll draw it like a stretch. Okay, so I'm thinking about the areas under these two graphs between A and B. Well, they're both rectangles, base and height. So the area of this one is going to be B minus A times f of x. And the area of the taller rectangle is going to be B minus A times C f of x. So whatever factor I've stretched the function by is going to be the factor by which I stretch the height. So it's going to be the factor by which I stretch the area of the rectangle, that factor by which I stretch the definite integral. Multiplying the function by C multiplies the area by C. Property 4. To integrate a function from A to B, f of x dx, and then to integrate it from B to C, f of x dx, is the same as just integrating it from A to C, f of x dx. So this is the first of the properties that we've looked at that has different limits of integration on some of the different integrals. All of the other ones we've done so far were all just from A to B, so over the same interval. Here, however, we've got the same function under each one. This one makes a lot of sense if you just think about the definitions. This is the area under the graph of f from A to B. This is the area from B to C. And this is the area from A to C. This is essentially just saying we can add areas. Here's the picture. So I'm going to label A, B, and C, and draw just a random function. It doesn't matter what f looks like. This will be true for any integrable function. And then let's shade in the three areas we have. So the integral from A to B is this region in here. And then we have the integral from B to C. That's going to be the region in here. If we add those two areas, we get the area under the graph from A to C. That's what this integral represents. Property 5. So this is just a comparison property. Suppose that we have one function that is always smaller than another function, g of x, on an interval. Then the integral over that interval is going to be smaller as well. Once again, let's draw a picture. Let's draw the two functions, the graphs of the two functions on an interval A to B. Now, we have to draw f below g. It's okay if they at some point have the same y value, in other words, if the graphs touch, but f always has to stay no higher than g. So maybe this is g. Maybe this is f. So the integral from A to B, f of x dx, is this. And the integral from A to B, g of x dx, is going to be that area plus some more. So it's clear that this integral is going to be larger than this integral.